Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. The halogens. Before moving on to the physical properties of the halogens, I'd like to highlight one source of error. When the word iodine is used in a description, say, of a practical procedure or in an examination titration calculation problem, that is referring to the molecule I2. All of the halogens form diatomic molecules. Similarly for bromine, Br2. So when in titration data you have a certain mass of iodine, it's crucial that you realise that the formula being referred to is I2. Bearing that in mind, can you calculate the relative molecular mass of each of the halogens? Pause the video, come back when you have done that. Well, let me share with you my calculations, and you will see that I'm quoting the relative molecular mass to 1 decimal place. Why? Because the data provided in the OCR periodic table quotes relative atomic masses to 1 decimal place. So you must reflect that in your relative molecular mass calculations. So 253.8 for iodine rather than 254. If I now go on to the physical properties and share with you the boiling points, you can see that they justify the states of these states for the halogens. Fluorine is a gas, that is, its boiling point is below 298 Kelvin. Similarly, chlorine is a gas, its boiling point is below 298 Kelvin. Bromine is a liquid, its boiling point is above 298, and iodine is a solid. So I haven't given you melting point data, but bromine is a liquid and iodine is a solid, a dark grey crystalline solid at room temperature. But what you should notice is that there is a trend down the group of an increase in boiling point. I'd like you to pause the video and write out an explanation in detail for why the boiling point of the halogens increases further down the group. Restart when you are ready. So check your explanation for the increasing boiling point of the halogens further down the group. I'm going to reveal my argument step by step. Have you in your argument put forward that the forces between halogen molecules are London forces, instantaneous induced dipole attractions? Have you put forward that the more electrons there are, the larger these instantaneous and induced dipoles formed are? Have you stated that the relative molecular mass of the halogens increases down the group and that therefore the molecules further down the group have more electrons? Have you made the link, that the logical link, but therefore the molecules further down the group have stronger instantaneous induced dipole attractions, or have stronger London forces. And if they've got stronger London forces, to overcome these stronger intermolecular forces, more energy is needed. That is, higher temperatures are needed. Check this against your answer. Moving on to electron configurations of the halogens. For each of the halogens, you have the atomic number. Could you write a shell configuration and a subshell configuration for each halogen in turn? Pause the video, come and check your answers when you are ready. So here are for fluorine 2,7 and the subshell configuration, obviously 1s2, 2p5, sorry, beg your pardon, 1s2, 2s2, 2p5. Then for chlorine 287 corresponds to 1s2, 2s2, 2p6, 3s2, 3p5. Bromine 28187, it's got 35 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 accounts for the 18 in the third shell. 4s2, 4p5. If necessary, have another go at iodine. Otherwise, I'm going to reveal 28187, justified via subshells. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, that's 18 in the third shell. 4s2, 4p6, 4d10, that's 18 in the fourth shell. 5s2, 5p5. Now if we look at each of those in turn, we see that the highest energy electrons, or the electron configurations in the highest energy shell, is S2P5 in terms of subshells. So we can write a general statement that the outer shell of a halogen will contain two subshells, and the configuration in subshells will be NS2 NP5, where N is the shell number. Moving on to the redox chemistry of group 7, and here in particular we're going to consider the gaining of one electron to form a negative halide ion. We're not going to consider the halogens in their covalent chemistry, which we looked at in bonding sections. So we can express that change as an equation that any halogen X, so that could be chlorine, bromine, iodine, etc., gains one electron to form the halide ion X-, Cl-. Now in terms of redox chemistry, what statements can you make about that change? Pause the lesson and write down your thoughts on what can be said in terms of redox ideas. Restart when you are ready. So there's two simple things that can be said. The halogen has gained an electron, so this process is a reduction. The gain of electrons is reduction. The other thing that can be said is if the halogen is itself being reduced, something else must be being oxidized, something else must be losing electrons. So the halogen is acting as an oxidizing agent. Now, just to finish up on this, I'd like you to write the electron configurations for a fluoride ion and for a chloride ion in terms of shells and in terms of subshells. Pause the video and check your answers when you are ready. So here are my answers. The electron configuration in shells is 2,8 because fluorine as an atom has 9 electrons but has gained an electron to become negative, so it's now got 10 electrons, so it's subshells 1s2, 2s2, 2p6. Similarly, chlorine as an atom has 17 electrons As an ion, it has 18, so 288, 1s2, 2s2, 2p6, 3s2, 3p6. These electron configurations here in shells and in subshells are the electron configurations of a noble gas. So these are stable electron arrangements. It is possible to predict the trend in reactivity down the group, that is down the group 7 of the periodic table, on the basis of first principles. Recall that we are in this context talking about the redox chemistry where the halogen gains an electron to form the halide ion. How easily is that electron captured? What is the trend in that ease as the halogen is placed further down the group? There are three factors to consider: atomic radius, inner shell shielding, and nuclear charge. How do the changes in these three factors affect the ability to capture an electron? I'd like you to pause the lesson, write down your ideas, and come up with a prediction for the trend in reactivity down group 7. So let's go through the ideas. So I'm going to compare fluorine to chlorine to start with, and I'm going to draw or write an electron just outside the atom to be captured. Straight away, obviously, the atomic radius of fluorine is much less than the atomic radius of chlorine. And that therefore would indicate that the nuclear attraction of fluorine for the electron to be captured is much greater. If we compare inner shell screening, chlorine's got 2 inner shells of electrons, fluorine just has the 1. So again, fluorine with less inner shell screening would be expected to have a greater nuclear attraction for the electron to be captured. However, if we consider nuclear charge, +9 for fluorine, +17 for chlorine, that would indicate that chlorine would have a greater nuclear attraction. However, as with our experience of ionization energies, exactly the same ideas, it's the atomic radius that is the key influence. And therefore fluorine with a much shorter atomic radius and less inner shell screening has a greater nuclear attraction for an electron to be captured, and therefore fluorine much more likely to form the halide ion than chlorine. And we would expect that trend to be repeated down group 7. Recapping on that idea and just tidying up, as we go down group 7, we need to consider changes in atomic radius, shielding, and nuclear charge. As we go down the group, due to an increase in atomic radius, the nuclear attraction is weakened. As we go down the group, due to there being more inner shells, the nuclear attraction is weakened. As we go down the group, due to an increase in atomic number, in fact, the nuclear attraction increases. However, the main influence is atomic radius, coupled with changes in inner shell shielding, means that as we go down the group, the halogen is less able to capture the electron, and the halogen is therefore less reactive. So we can use the ideas of differences in halogen or trend in halogen reactivity to explain halogen-halogen displacement reactions. So let me show an equation to discuss. Well, here we have aqueous bromide ions and aqueous chlorine molecules. Chlorine has a greater tendency to form chloride ions. It's more reactive than bromine, and therefore the product of the reaction is chloride ions, and bromine is changed to bromine molecules. So chlorine, being more reactive, has displaced bromine from its compound in solution. Chlorine has a greater tendency to form the chloride ion than bromine has. Could you rewrite that equation in the form of an ionic equation? Pause the video, come back to check your answer. Here is the correct ionic equation. Two bromide ions form bromine molecules, two chlorines form two chloride ions. What's happened to the potassium? Well, potassium is in the form of an aqueous positive ion in the products and is in the form of an aqueous positive ion in the reactants. So therefore it has not undergone any change. It is spectating, and spectator ions are omitted from ionic equations. But can you rewrite that ionic equation in the form of redox half equations? Pause the video, write your half equations and come back to check their accuracy. Here are the oxidation of bromide ions to bromine molecules through the loss of 2 electrons. So bromide ions loses 2 electrons, 2 bromide ions lose 1 electron each to form the bromine molecule. And the chlorine molecule gains 2 electrons to form 2 chloride ions. That is reduction. So here's a very similar problem. Aqueous bromine water, is added to an aqueous solution of potassium iodide. Could you complete the reaction equation, rewrite it as an ionic equation, and then represent the ionic equation as 2 redox half equations? Pause the lesson, resume when you are ready to check your answers. So here is the completed equation. And as an ionic equation, we leave out potassium. It's spectating. Potassium ions, I should say. They are spectating. And then 2 redox half equations. Well, iodide loses 2 electrons, so that is oxidation to form iodine. And of course, bromine gains 2 electrons to form 2 bromide ions. That is reduction. The OCR specification includes in the additional guidance the colours of aqueous solutions of the halogens, and they're used to predict colour changes in displacement reactions. So you are expected to know that chlorine is pale green, probably not as intensely green as that in a solution. Bromine is orange, again that is quite a concentrated solution, and iodine is brown, again quite a concentrated solution, but those are the solution colours included or described in the approved textbook. So the other thing to note is that all aqueous solutions of metal halides, potassium iodide, sodium chloride, are colourless. You might be asked to describe the final colour when, here's 3 examples, chlorine water is added to potassium iodide solution. What will be the final colour of the solution? Similarly for the other 2 problems, bromine water added to potassium chloride solution, bromine water added to potassium iodide. Think it through and write down the final colour of the solution, obviously referring to the colours here. Pause the video, think it through, come back to check your answers. So we have brown as a final colour. Now how can that be? Well, chlorine water is added to potassium iodide, so chlorine is more reactive than iodine, so iodine will be displaced, so we will get iodine being formed, a brown solution. If we look at the next one, bromine water added to potassium chloride solution, well, chlorine is more reactive. Chlorine is more reactive than bromine, so no reaction will take place. So there's no change. So the original orange colour of bromine will be maintained. There will be no change to the original orange colour of bromine water, because chlorine is more reactive and therefore bromine will not displace chlorine from its compounded solution. If we look at the last one, bromine water is added to potassium iodide. Well, bromine is more reactive than iodine, so we would expect bromine to displace iodine, and therefore we're forming iodine solution, which again is brown. There is an added complication in halogen chemistry in that the colours in organic solvents such as hexane are different from the aqueous solution colours. We'll see here that chlorine in an organic solution such as hexane is quoted as pale green, is likely to be more intense, more obviously coloured than an aqueous solution. Similarly for bromine, you're likely to see an intense orange colour. For iodine, there's a completely different colour in hexane compared to in aqueous solution. It is violet. So the sorts of problems would be exactly the same. Describe the final colour in the organic layer, I should add, when chlorine water is added to potassium iodide solution and the mixture is shaken with some hexane, and then bromine water is added to potassium chloride solution and the mixture is shaken with some hexane. So that's the sort of thing that you will be doing or will have done in the laboratory. Simple test tube displacement reaction with the addition of an organic solvent such as hexane to help with the distinguishing the products. Pause the lesson and complete the two final colours. So as chlorine will displace iodine, we would see iodine in the organic solvent, and that would be the colour violet. As bromine is less reactive than chlorine, there'll be no change chemically, so bromine will remain and will be collected into the organic solvent, and therefore you would see a strong orange colour. So let's move on to looking at how water supplies are made safe to drink. Central to that is the reaction of chlorine with water. There are in most textbooks more than one equation for that reaction, but OCR A specification is very particular. It's cold water only, for which this is the reaction equation. You'll see there are two chlorine containing molecules as products, and obviously the reactant chlorine. I'd like you to pause the lesson and work out the oxidation number for the chlorine in each of the chlorine containing molecules. Restart when you've done that. So here are the oxidation states, oxidation numbers of chlorine. As an element 0, in HCl we have hydrogen at +1, a rule, chlorine therefore -1. HClO, hydrogen plus 1, oxygen minus 2, a rule. Therefore, to sum to 0, chlorine plus 1. Now, how might we name the products? Well, HCl, I hope you realise, hydrogen chloride or hydrochloric acid. Would you like to pause the video and try and name the second product, HClO? Restart when you've had a go. So, the combination of chlorine and oxygen is known as chlorate. And obviously we need to identify the hydrogen within the molecule, so hydrogen chlorate, but we also need to add the oxidation number of chlorine within the molecule as a Roman numeral, so hydrogen chlorate 1. Moving on to the oxidation number changes, we'll see that one of the chlorine goes from 0 to -1, and that is a reduction, whereas the other chlorine goes from 0 to +1, that's an increase in oxidation number, so that is an oxidation. So chlorine is both simultaneously oxidized and reduced, and there's a particular word used to label reactions, redox reactions like that, and it is disproportionation. So disproportionation means that within the reaction the same element is both oxidized and reduced. You are expected to know and use the term disproportionation. You'll also notice that in the equation I've used an equilibrium sign. The equilibrium sign means the reaction is reversible. We have all 4 molecules present together at any one time, and it is thought that the equilibrium lies to the left, which leads to the conclusion that from the reaction of chlorine with water, the concentration of hydrogen chlorate 1 is quite low. However, it is the hydrogen chlorate 1, or the released ion, the chlorate 1 ion, that is the bactericide in water treatment. It is not chlorine Cl2 itself. It is the product of the reaction of chlorine with water, hydrogen chlorate 1, that kills the bacteria. As you know, there are some risks associated with chlorine. Chlorine is a very toxic gas, and escape of chlorine would be very hazardous. Chlorine reacts with hydrocarbons to make chlorinated products which may or may not be toxic. So there are some risks associated with using chlorine in water treatment, but this is where you are expected to weigh up risks versus benefits, and to the general health of the public, the benefits of the bactericide action of hydrogen chlorate 1 far outweigh the possible risks of chlorine toxicity and any chlorinated hydrocarbon products. Chlorine reactions are also used in the commercial production of bleach. So here the reaction to consider is the one between chlorine and cold dilute alkali. Again, you may find different reaction equations in textbooks, but we're looking at cold dilute alkali to form the chlorate 1 ion. Chlorine and sodium hydroxide has been set out for you. You complete the equation, please. Pause the lesson and complete the equation. Come back to check your answer. So here, if I reveal the correct products, we have sodium chloride, NaCl. So we've got Cl- and ClO-, so we've got the chlorate 1 ion here. Now we need to balance up, so we've got a hydrogen on the left-hand side, so we must have a hydrogen on the right. You'll notice the total charge on the right-hand side is now 0, plus 1 for hydrogen, minus 1 for the chlorate 1. NaCl is neutral. The left-hand side is neutral. So we realise that we must have a product of H plus to balance the equation both in terms of atoms but also in terms of charge. The total charge on the left hand side must equal the total charge on the product side, and that is now the case. Now, because this reaction is not an equilibrium, the concentration of chlorate 1 ions is much higher than that produced by the reaction with water. And therefore, the reaction is used commercially to produce household bleach. Chlorate 1 has bleaching properties. The higher the concentration, the stronger the bleach. So by reacting with sodium hydroxide, you get a higher concentration of chlorate 1 ions and therefore a bleach that can be used commercially, or sold commercially, to be used in the household. However, the reaction for that is normally written with 2 sodium hydroxides. Could you complete that equation? So we've got 2 sodium hydroxides to account for, so rather than forming the chlorate ion, we're going to form sodium chlorate. So rather than the chlorate ion as in the first reaction, we're going to form sodium chlorate, so we're now balanced for sodium ions. And we have an additional hydroxide ion which is going to react with the hydrogen perhaps to form water. So this is the more usual way to present the reaction of chlorine with sodium hydroxide, with a product of water rather than a free H plus ion, which in the presence of an alkali is going to be forming water. So you are expected to be able to reproduce both reactions, equations, depending on the circumstances of the question. To avoid repetition, the characteristic reactions of the halide ions, the test tube reactions of the halide ions, is covered in my lesson 3.1.4, qualitative analysis. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.